So yeah, I'm Nathan. Thanks for the introduction. Alice and Coco, thanks for hosting. Super excited to be here. I'm an engineer on the SP1 team. Today I'll be showing you guys how to build Tornado Cache with SP1. Ideally less than 30 minutes. Kind of the way that this will go is that I'll do some preliminaries, explaining what is zkVM, what is SP1, what is Tornado Cache, and then I'll explain how Tornado Cache works. And then there's a repo where everything's already finalized, but I'll actually be live coding the program and the smart contract. We can do it together. So yeah, let's jump into it. What is SP1? SP1 is what we call like a zero-knowledge original machine, which is a piece of software that accepts as input another program, as well as the input to that program, and outputs the output of that program, as well as like a small receipt that very like cryptographically proves that the execution was done correctly, and basically ties that proof and the output all together. And Tornado Cache, you probably all know about it, is like this piece of software that basically gives you private transfers of blockchain. And this is like really powerful because before ZK was like feasible, the only way to get like privacy on chain was to just like trust some guy and send in the funds, and eventually you would ask to withdraw, and you would just have to trust that like he doesn't really or. So I promise only slide with math on it. But what is a ZK proof? ZK proof starts a claim that says some monomial f is 0 or Fausto domain. And if you don't know like a field is, you can think of it as like the integers from 0 to some large prime. And we care about some like smaller subdomain, such that it's all 0. And there's an interesting fact called the Schwarz-Siebel lemma that basically says if you randomly sample this polynomial at a point of the domain, then the probability that it's like randomly 0 is the degree of the polynomial divided by the side of the field. And like what's really interesting about this is like pretty much most deterministic programs can actually be compiled down into like a set of constraints that end up looking like this polynomial. So we can prove things about the program, re-execution, as well as the output, and basically sample as many times as we want until we get like the guarantees that we care about. And so you can think of a proof as just spot checking that a polynomial is 0 on some domain, and the actual like zero knowledge comes from how you do the spot checking, which means like how do you commit to the polynomial rather than like how do you actually check it. And so like why does this matter? And like tools like Tornado Cache are the only way to get privacy on chain. Like there's like some other schemes, but really everything kind of will say Tornado Cache. Everything basically looks like taking an anonymity set, putting which people together, and doing a proof that you're actually like are own a deposit in that set. And the original Tornado Cache implementation was like pretty complex. We had to use like custom ZK circuits. You had to like write everything by hand. You couldn't use like the most efficient hash functions that exist on chain, and you kind of had to do like a bunch of math to actually make it work. And now you can use like these really efficient hash functions, and you can write your circuit or like program in Rust, which is like much faster than like using like CirCom or like any of these other like specialized ZK tools. And yeah, so now I'm gonna go into like a construction of like what we're gonna be doing today. And so the first part is like understanding what a Merkle tree is. A Merkle tree is like this like big data structure that lets you like insert pieces of data and generate these like short proofs that are based on like hashes. That's something that's actually included in the tree. And what's nice is like you can take as many pieces of data as you want, and you can represent them by a single hash, which is like very nice. And like if you did care about privacy or efficiency, you could use this to like manage deposits in a smart contract where if I make a deposit, you insert it into the tree. When I want to withdraw, I just submit this short proof that you can kind of see. In order to actually prove that like TE, which is maybe my deposit, is included in the tree, I just need these like 5 hashes. And there's like a very short protocol you can run to check that it's actually included in there. And so you can hopefully see how that works. Is there any questions about like how this works? This is kind of a big report. Sweet. Very cool. So now how does the protocol work? Basically when you deposit, you're going to submit something called a leaf, which is chosen here. This just means take a 32-byte secret key, take a 32-byte nullifier, to condense them together, it's 64 bytes, hash it, and when you deposit, you submit this thing called the leaf, and on chain, the smart contract will insert this into the Merkle tree. And this is all the like on chain, and in the clear area, we can see that this leaf is actually equal to the tree. And now when you go to withdraw, basically we're gonna submit the hash of the nullifier, as well as like a short proof that basically proves that I know zkNN such that it hashes to some leaf, and that leaf is actually equal to the tree. So yeah, in other words, the circuit will like compute the leaf hash, verify a Merkle proof, and it'll commit to like these outputs, which are the root and the nullifier hash, and the root and the hash are on chain, and so this can all just be checked very nicely. And yeah, so now I want to explain a little bit about like what programming with SP1 looks like. It's kind of with the array paradigm. And so we have the concept of precompiles, and precompiles are like these specialized circuits. Generally they're for like cryptographic operations. So we have things like elliptic curves, hashing, field arithmetic, RSA, signature schemes, like all types of stuff. And they like hook it to the VM and hook it to these like specialized circuits that are like much faster to prove than if you were to compile your program. Like say you're doing a hash, you could theoretically compile this to like recycles, but ideally you have like a specialized circuit that is much faster than proving a bunch of recycles in a loop. And the other cool thing is we maintain these things called patches, which basically override the default. So you might have like a program that already exists that maybe like verifies the signature, and you have these things called patches, which will override the default behavior and hook into our precompiled infrastructure. So that way you don't actually have to change anything in your existing code to actually get it to work in SQL and able to work efficient. And yeah, we also have what we call the prover network. We've done a ton of work to make this like very fast. We have a bunch of GPUs online. We also have like quote unquote permissionless proving that's coming online soon, where anyone can participate and become a prover. And it's like very fast. It's much easier to use the prover network than it is to set up a bunch of GPUs yourself. And yeah, if you're interested, you should reach out. We also offer like enterprise plans, which are cheaper than the public one, and we have like very tight performance SLAs. So yeah, and I said I'm gonna be basically coding the program, explaining a little bit how it works. The stack is pretty straightforward. It's just SP1, which is the zkVM we talked about, and Alloy, which is like this nice library that lets you plug it as like EVM chains. The repo's on screen. I'll leave it up for 15 seconds, and then we'll get to. Obviously, I'm gonna move over to that now. Is this all? Basically, we're just all. Can I just do that? So I could like. Sorry. And very cool. So yeah, this is the program we're gonna be doing. I already have a bridge here. I might look at it occasionally. And so the general structure of like an SP1 program has like 4 parts. It's the host, the program, the contracts. And so the host is like actually what generates the proof. The program is the thing that's run inside the zkVM and that you're generating your proof of. The contracts are, assuming you're doing an on-chain deployment, the contracts are the thing that actually like accept the proof and do some business logic on-chain. And then the Merkle live is something I wrote, but generally you might have like a small library that has some like shared functionality between your hosts and your programs.
Can you increase font size?
Yes, sorry. How's that?
Better. Thank you.
Sweet. So yeah, I have this written already, and it's like in the repo if you want to run it. There's instructions for you to run it now if you'd like, but I would just be kind of like through like kind of step by step how I would think about writing it. So the first part, unfortunately, is always the boilerplate, always fun. So to add this so we can actually run it. Yes. So this entry point macro here takes in like the argument of like the actual entry point of the program. This sets up some stuff that the zkVM needs. Like when we exit, we want to like constrain the exit code and stuff. So that's what that does. And so the first step is like thinking like, okay, if the thing that we're proving is like that we know the preimage of a hash is actually included in the Merkle tree. And so like to think about what that looks like, you probably want the secret key, it'll bit. And so in SP1, we have this thing called IO read, which will read from the standard in. And then we gotta do this type. Okay, and then now that we have like the secret key and nullifier, and since this is running in the program, like this is all gonna be secret when it gets inputted. And so we would sit down. Okay, so the first step, as mentioned, is actually just computing the leaf. And so this takes in the secret the nullifier, computes the leaf that we're claiming is in the trees, and the trees hash that. You start reaching. And then the second step would actually be verifying the proof. And so, as I said, this is verifying the Merkle proof. So this is verifying that given some roots and the leaf that we just computed, as well as like the index where the tree does actually live, that we know that this leaf is like very likely to put it in the tree, like a very high probability to go to the tree. And yeah, the last step is committing to the outputs. And we'll explain a bit why we actually commit to the outputs. But the things we're committing to are the hash and the root. And so the hash is this thing that we're going to be like giving up. And the reason we want to like actually commit to a hash is that so we prevent double spends. So when we withdraw from the pool, we want to make sure that someone can't just keep calling the same, like somebody with the same proof and like withdrawing the same thing they already withdrew. And so now it's contract. Actually, did anyone have any questions about like how the program works? Like this is the full program. It's in program/short/main.rs. Did anyone have any questions about that? Yeah.
Essentially, it's calling verify proof in the program that this is the proof.
Right. So there's two proofs, and yeah, this is my fault. There's two proofs going on. One is like the zero knowledge proof of like the program itself, and the one is like the Merkle inclusion proof. Yeah. So in the zkVM, we're verifying a Merkle proof, and then we create like a big proof of that whole program that does more than the one thing. Yeah. Yeah.
So I see that you're using node hash on the way in and then nullifier hash on the way out. Is that kind of roughly thought of as like you're submitting a public key in the lay in and then you're withdrawing right in the layout?
I think it's like you're committing to a secret, and then you like reveal part of that secret. Yeah. So I guess like one way to think about it is like if you didn't care about privacy and stuff, I could submit a hash and like a lockup, and then to withdraw, like I could submit the preimage, or I could submit like the input, hash it on chain, and then like that means like I like yeah.
Anyone else? Any questions? This might be later, but we said that this is CJ input.
Exactly. Yeah. So, it like this part, and I'll show you more in the contract, but this commit part is actually the thing that is known as like the public outputs, and then the input itself, like the thing that we read here, can be kept secret. Yeah. So nobody knows this. Yeah. Sweet. Move on to the contracts. So yeah, this just like last time. So yeah, I've gone ahead and actually made like these Merkle tree libs. I won't be going into like how those work too much. It's a pretty common pattern. So that's why we won't be focusing on them. So the first step would actually be so in smart contracts, if you guys are familiar, there's this term of this thing called the constructor. This is what's ran when the contract is first deployed. And so when you deployed an instance of this contract, you need to give it another contract, which is the SP1 verifier. And this thing called a V key. The V key, also known as the verifying key, is a thing that actually like ties your proof to a specific program. So you can't just submit any proof. You can't just submit any program to like be verified here. You always need a V key as some input. And so this also sets up the deposit amount and creates like this industry tree. The deposit function is like very, very simple. The deposit function checks first, and it's literally you mark things as payable. And so the first thing it checks is, are you depositing the correct amount? If not, like throw failure. And then it inserts your node hash into the tree and returns an index. And now off chain, instead we have these things called events. Off chain, you can collect all these events and rebuild the tree, so that way you can create a proof out of it. And so this emits an event so that we can do that. And then fine. The withdraw function. And so the withdraw function takes in two arguments: the hash of the nullifier and the proof. Kind of off topic, but the reason we give the nullifier hash and all the nullifiers because it would like lower security, and you'd be able to like search the tree faster if you actually had the nullifier, because it would only need to know it's 32 bytes. So we give the nullifier hash, and we check that it has already been spent. This is the part where I was talking about where we prepare double spends. The second step is we actually mark in the state that this nullifier has been spent. That way it cannot be used in the future. And then, if you guys remember from the program, we have this thing called proof commitment. And so we know on-chain what the root should be. So we just plug that right. If we take from the on-chain state, the root, and plug it into the proof commitment type. And then we have the nullifier hash, which is passed in as a user parameter. And now we pass this directly into the verify proof function, as well as the B key that is hard-coded, and the proof supplied by the user. And if this fails, this will like stop execution, and then this will happen. All the state will be reverted. But if it passes, then we know that they actually submit the valid proof that shows that they know a leaf in the tree with this nullifier, and that we should send them the correct amount. Yeah, and then off-chain, I will actually be like, I'll just be kind of cruising through these parts. These are just like very straightforward like on-chain interactions that you could do with Alloy. So we deposit, we go ahead and create like a random secret key every time. We create a random nullifier. We hash them together, as we said, with the notes. It's called the notes. And then to deposit, set our values to 1. We pass in the note hash, and we read the index from the log. So this is, as I was saying, so if it's events, we read it from the events. And for like this demo, we're just writing it into this file called milk.bin. And now on withdraw, pretty similar thing. We set up the SP1 prover, and the SP1 prover, we expose this like they call the SDK, which makes it very simple to actually use the prover and direct proofs of like arbitrary programs. And so the first step is to create a prover and set it up, as well as get the EM provider. We read the note from storage. From it, we parse out the secret key, the nullifier, the index. And down here we're setting up the actual contract inputs. I mean, the program inputs, sorry. And so as you remember, the program accepted this thing called proof input, which is the secret and nullifier of the brew and like the Merkle brew. And we just write that into what we call the standard in. And this is the thing that's actually going to get passed to the program that we're proving. And then with the SDK, we could just call prover.proof. We pass it this thing called the proving key. And so the proving key actually commits to just like what the program looks like, what the program does some pre-processing. And so all of it is contained, like, the entire like executable essentially is contained in the proving key. And we call Plonk, which is a type of proof system, which is like zero knowledge. which I'll touch on in a bit. And this thing returns an SP1 proof of public values. From there, we can actually get like the on-chain proof bytes. So this thing will create like a string of bytes that is like friendly that we could put on chain. And the last step is like hashing the nullifier. And because this is what we're going to submit as input. And yeah, so withdrawal, we just call the function with the nullifier hash and the proof bytes. And yeah, I said a lot of stuff. So if anybody has any questions, just like them.
Why did you guys choose Punk for this?
No trusted setup. Yeah. And so, yeah, I guess that is a good segue to basically SP1. We focus on creating succinct proofs, which are non-zero knowledge. And in order to get zero knowledgeness, we actually wrap them in a proof system that supports zero knowledgeness of verifying an SP1 proof. So it's like recursive proof verification such that we can get zero knowledgeness. And the reason we do that is it's much faster to generate these like succinct proofs. And then at the very last step, you get zero knowledgeness, which takes a little longer. Yeah. Any other?
In your SP1 program, you had like, or are the outputs always public?
Yeah, so you can choose to do no public outputs. Like you can choose to not commit to anything, which is like this explicit call here. But usually like most programs need some type of public output to like tie it to. Yeah, like to be semantically correct.
So you could, instead of committing, just dump it out, but it's not very.
Yeah, because if you didn't commit to the root, or if you didn't commit to like the nullifier hash or the root, then I could pass in any root and I could pass in any nullifier. And like kind of hard to prevent it. Double spend and stuff. Good. Any other questions? Yeah.
The way that's set up, there's no partial withdrawal, isn't that right?
Yeah, so with most privacy pools, you don't want partial withdrawals because that would... Actually, that's a good point. You can do partial withdrawals, but everyone needs to deposit the same amount. So it is a little... Yeah, it is interesting. It's definitely something that's possible. Yeah, that's a good point. So, yeah.
Using the same kind of workflow, let's say there's a random lottery or both for cash, and onboarding the system, proving security case is done. And there's a large deposit made by North Korea. And the entire chain it was onboarded to, let's say, our term is shut down, and is required to prove that you weren't that deposit.
Yeah.
Will that be had to do the box?
Well, definitely. I mean, I'm sure if you've been keeping up with the actual Tornado Cash case, this is like something they're actually talking about in the court right now, which is quite interesting. But yeah, basically kind of come down to like this thing called a sparse Merkle tree. So a regular Merkle tree, you can prove inclusion very easily. A sparse Merkle tree, you can prove non-inclusions. And so you can basically prove that, like, if I have like an OFAC sanction list, I can make a sparse Merkle tree out of it and prove that my deposit address is not included. But yeah, it's that possible.
Yeah. So I guess this is specific to proving network you guys have, but how would I have private inputs if I just send it to you to prove it?
Yeah, that's a really good point. Great call out. So there is no private inputs at the moment if you're using our prover network. Kind of the direction we're looking to solve that is using like T's, where you would encrypt to a T, and the T would do, because a lot of T's are actually GPU enabled now, which is kind of like the big sell of our prover network is we use like GPU for acceleration. And so yeah, eventually we want to run the prover in a T such that you can encrypt your inputs, your private inputs to the T, and like in theory, as long as the T is secure, then so are your inputs. Yeah, it's a good point. See. Any other question? I can try to run it, Ava.
So the idea here is you just deposit smart contracts non-privately, and then sometime later you make a proof SP1.
Exactly. Exactly. That's exactly right. Yeah.
When I do the proven at Midwestern, must the local curving kinds I do was branded on your laptop.
Yeah, I can. It depends for what kind of proof. If you're generating like a long proof, which we are, it's about a minute 30, I think. Yeah. And this is kind of, I think this is a class federation master also. Yeah. Sweet. Any other questions? And I'll try to run the demo. Okay, sweet. So yeah, there's also steps to run the demo yourself locally if you'd like. And yeah, so the first step is deploying, which with Rust Palatine is training.
I go back. It's the question. What?
Yeah, absolutely real time.
And answer the question about partial withdrawals. Seeing if you percent at private pools, you don't want to allow partial withdrawals, so then you adjust it and say as long as the deposit sizes are equal that you can. Can you elaborate on that?
Yeah, I mean, there may be more to think about, but like the key part of these privacy protocols is like the deposit size. And the reason is if you could deposit like arbitrary amounts, like on Ethereum, for instance, we like have accuracy up to like 18 decimal points. So if you deposit like very specific amount at like some time t at like any other time in the future, you withdraw that like very specific amount, we know it's you, right? And so it's like very important that the deposit sizes are the same. In terms of like partial withdrawals, seems possible. Like there'd have to be like some extra accounting and like change to the proof where it's like you prove that you own a deposit that has a bit coolly withdrawn somehow. But yeah, I have to thought about that.
So enabling partial withdrawals is more like an operational question, not privacy.
Yeah, definitely. That's what I did. But yeah, the deposit size is really the key to gaining privacies. Yeah. And like having a bunch of people deposit the same amount, right? Because the more people that deposit, the bigger the like the anonymity size is. Yeah.
Okay. Thank you.
And so yeah, that's the deployment. And then to deposit is like another script. I'll just do like 3 deposits to create a bunch of privacy. And then yeah, the last step would be co-withdraw. And what this does is it scrapes all the events that have been emitted on chain, builds a local Merkle tree, and you can see that the local root under contract root match. Like I said, this is gonna take a minute 30, so I think I'm gonna cancel. But if it did work, this is kind of what it would look like. You'll see some like information about DAO and Flonk circuits, and this happens after like the core proof types have been created, the Succinct to the not zk proofs, and then we wrap it into a Flonk proof and submit it on chain, and you can see here that it was successful. And yeah, it's pretty much the end of it. Is there any other questions before I wrap up? All right.
Is that a call for questions? Last opportunities. All right, well, let's give it up for our first available. Maybe.